Hello, how's it going? All right, so in the previous session, we made a shader and got it working. And then we concluded by briefly throwing in a class that we didn't look at, treated it like a black box, and said it represents a triangle. There we go. Okay, now the job of that triangle class was to declare data and send it to the GPU, and that's what we're going to look at today. By the end of this session, we should be pretty confident in sending data to the GPU. All right, so I guess the first thing to talk about is screen coordinates. Why not? It's good to be confident with it. So the way screen coordinates go, I'll just open up this triangle mesh, and today's session is going to be semi-guided in the sense that I'm not going to be writing every single line top to bottom. That gets a little tiring, but code is linked in the description down below, so hopefully you can get in there and see what's happening. So here we start with a bunch of data, and these first three attributes are the x, y, z coordinates of each point. Okay, so the convention with x is that an x value of 0 is at the center of the screen, an x value of -1 is all the way on the left. So if I were to run this right now, here we have RGB, so the red point would be all the way at the left of the screen. Let's give that a go. There we go, all the way at the left. Okay, now with Y, 0 is at the center level of the screen, 1 is at the top of the screen, and -1 is at the bottom of the screen. So what I'm going to do is I'm going to modify these points so that I'm covering like the bottom left triangle of the screen, if that makes sense. So this one, I'm going to call it the bottom left. So we'll go all the way down to the bottom. This point here, let's go bottom right. So we'll go to the right, x equals 1. And then at the bottom, so y equals -1. Excellent. And this point here, currently x is at the center. I'm going to make that the top left. So we'll go left side of the screen, x equals -1, top of the screen, y equals 1. So again, it's a good idea just to mentally check what we expect to see. I expect that in fact, I'll label them. We'll go bottom left should be red, bottom right should be green, and top left should be blue. Okay, let's see if that happens. It might not. Oh yeah, there we go. Excellent. So then the next question is, all right, so by the way, this is called NDC, Normalized Device Coordinates. And the reason for that should be clear. It's normalized. So -1 always means the left, +1 always means the right for x, for instance. That's independent of the screen size. So a pretty reasonable question to ask is, how does OpenGL know basically how big the screen is? Now, I believe that, I haven't looked into this, but I believe if we look up the main, here we go, when we make the window, we declare how big the window is, and then we tell GLFW to make that context current. And what that does, I believe, haven't looked into this, is it configures the window size, basically, the viewport size. But we can set that by hand as well. By the way, the reason I've got Google up here is that this IntelliSense isn't so good, so I may be Googling things, and that's a great practice anyway. So what are some cases where we create a window, but the default configuration doesn't match? Well, for instance, if we're running this on Mac is a little weird with its sizes. Sometimes it has this sort of double pixel thing with pixel density where it actually turns out being half the size. Or if you're running a program in tandem with another frame capture program like Zoom, it might just mess with the defaults. So totally fine. What we can do is we can query, here's all my past searches, glfw get frame buffer size. There we go. It's great practice just to be in the habit of searching documentation always. So yeah, it's this function here, get frame buffer size. We take in the window, and we take in pointers to integers which are going to be populated with the frame buffer size. So we can go down here and say, all right, I want to get the width and height of the window. Let's go ahead and do that. glfw get frame buffer size, pass in the window and the address of those variables, and they will be filled in for me. Okay. The next thing I can do is I can use that information to set the viewport that I want to render to. So I'll say, all right, GL viewport, and the way this goes, whoops, that's a lowercase p. The way this goes is we have the coordinates of the top left region that we want to render to, and then we have the width and the height. So this is just double checking that the frame has been set up correctly. So we can go run that. Ha ha ha, what's happened here? Oh, that should probably be a capital G, I think. There we go. Okay, nothing happened because it was set up correctly initially, but we can double check by forcing it to be incorrect. So let's say I want this to be 200 by 200. Give that a go. There we are down there. And what happens? So interestingly, the whole frame is being cleared properly. What happens if I want to set this at an X of 100? Yep, it's offset there. And then, okay, so I'm just playing around with this. Right, so OpenGL thinks that it's drawing the whole screen right now because the viewport has been configured. But we set it. So it's at an offset of 100 in the X, an offset of 200 in the Y. So it's up here, and it's just that little 200 by 200 region. Okay. So let's never do that again. But there are cases where you might want to do this. For instance, if you're rendering like a region, like a little viewport, but you don't want to go through the trouble of creating your own texture to render to, you can totally just fake it with viewports. All right, so there's that. But now I'm going to go on to two really important definitions, because we are going to get to the stuff. So we go back to the triangle. We have all this data here. And the two definitions I want to get into are vertices and attributes. So I'll just refer to my notes here. All right, don't want to get this wrong. Super important. So an attribute is a set of 1 to 4 numbers describing something. So in this case, we've got an attribute for position. There we go, X, Y, Z. 3 numbers, all floats. An attribute for color. There we go, RGB, 3 numbers, all floats. Okay, but some other examples are texture coordinates, normals, and you can even have heterogeneous data. So that was all floats, but you can have integer data. For instance, if you want to store which light index is going to be working on a particular vertex, you can do that. There's nothing stopping you from doing that. If you're doing skeletal animation, you could save in the integer index of the bone, which is going to be influencing this vertex, and you could have several of those, for instance. So when we think attribute, just think of, a set of numbers which describe an aspect that we're gonna, and it's an attribute. It's a recursive definition. Okay, and the other one is a vertex. So the reason this is super important is a lot of people think of vertices as X, Y, Z, or maybe just X, Y points. And yes, those are vertices, but in OpenGL, a vertex is a collection of all the attributes needed to draw a point properly. So here we've got, this is a vertex. It's a collection of 2 attributes, both having 3 elements, 3 numbers each. There's another vertex and another. So we can see, yep, we have 3 vertices. Now, if you look at this loading code, this stuff here with the VAO, this is a little funky. But I want to just look at this stuff down here with the VBO. So this VBO stands for Vertex Buffer Object. Now, a buffer, just think of it like a list. It's a whole big list of data. So what we do is we get all of the vertices that we want to draw, and we send them to a buffer, and that buffer gets shipped off to the GPU. Okay, so that's what we're doing down here. We say, okay, this stuff is, if we go over to the header, this has been declared. All of these resources are referred to as unsigned integers. So under the hood, when we say make a buffer, the graphics card allocates a chunk of memory, it manages it, and it just gives us back like a handle, like, hey, this is buffer number 2, this is buffer number 7, or something. So that's the reference here. That's what that is referring to. And then over here, all right, so we generate a buffer. Again, this is just the same as before, pass a reference to the integer, and that gets filled up with the relevant number. And then what we're doing here is we're binding this, and I think of this as like you're in a studio and you've got a bunch of workbenches. So this is like, you know, put this on table number array buffer. And then later on, we don't refer to the VBO, we just refer to, hey, I want to do something to an array buffer. And that is the table that we're working on. I hope that makes sense. But yeah, so this part here is just sending that data over. So we have the target that we're sending to, which is the array buffer in this case. And then we have the number of bytes that we're sending. So this is a vector. Size will indicate the number of floats in the vector. And then we want the number of bytes, so we multiply by the number of bytes in a float, which is 4, because it's 32 bits. Now, this next argument is the pointer, which refers to the location in memory where all that data is stored. So with a standard vector, std vector, the data function returns a pointer to the beginning of the data. That's it. If this was an array, we just pass it in just the same way you work with arrays. Now this next part, these attributes, are another super important bit. So remember in the previous session we made a shader, and in the shader we specified locations for these attributes. Now what we've done here is we've lovingly crafted this together, but when the GPU sees that data, it doesn't know how to extract the attributes from the vertices. Even worse than that, it doesn't even see numbers, it sees ones and zeros. It doesn't even know what the format is. And so that's what we're doing here. So this first number here is the attribute number that we're working with. So position is attribute 0, down below, color is attribute 1. This next part is the number of numbers in the attribute, basically. So as I said, they're both 3 elements each, 3 things each. Then we have the data format. Okay, fair enough. Now this part here is a little funky. This is indicating whether we should normalize these. In fact, let me just search this. So this is GL vertex attrib pointer. Okay, so there we have it. So yeah, we have the index of the attribute. Fair enough. Okay, normalized. So this data could be normalized or not. We're never going to do this, so this will always be false. This next bit is the stride in bytes. And that is the number of bytes that we will have to step forward to get to the beginning of the next attribute. Or I should say, the same attribute for the next vertex. So for instance, here we are at the start, and we will have to step through 6 floats to get to the next vertex. 6 floats, 4 bytes per float, so that's a stride of 24 bytes. This next part is the offset to the beginning of the attribute. So here position is at the start, that's an offset of 0, but then down below, when we get to color, color begins 3 floats into the array. So 3 lots of 4, color has an offset of 12. Now, I'm not going to talk too much about it, but this is a common mistake. See here, the next line is GL enable vertex attrib array. And if we look up the documentation for that, we've got enable vertex attrib array and then enable vertex array attrib. Oh, okay. So I won't talk too much about it, but the short story is that this is a versioning issue. So in later versions of OpenGL, they brought in something called direct state access, or DSA. And for those functions, they basically use the same names, but they varied the names a little bit. And this is my number one pet peeve with OpenGL, is that they didn't vary the names enough. That's messed up. And don't worry too much about direct state access. From everything I've used direct state access, it's not a big deal. It's actually a little bit less performant than what we're doing here, but it is semantically meant to be friendlier. And I don't care about semantics, so we're just going to go with this. Okay, so that is what we're doing here. We're just creating everything. Now, it's probably time to talk about VAO. Now, a VAO is a vertex array object. What does that mean? Great question. What does that mean? So I want you to think about when you're making a vertex buffer, I want you to think about it like this. A vertex buffer is the data, the raw dumb ones and zeros, in addition to the attribute pointers, which are indicating how to interpret the data. And what a VAO does, we can think about it like this, is it wraps up all of the state needed to draw this stuff. So the VAO will actually be recording the vertex buffer or buffers associated with this thing, as well as its attributes. So when we come to draw this thing, all we need to do is bind the VAO, and that will actually recall the data and its attributes. So that's it. It's just a weird thing. That's it. So again, I'll just give this a, and there we have it. Isn't it cool that we're doing all this stuff? But we can do a little bit more. So one option we can have is to actually separate these attributes out into different arrays. Now, why would you want to do this? Fair question. In most cases, having the attributes interleaved, linked together as tightly as possible, is best for performance. But there are cases when it's not possible to have them interleaved. For instance, if we are working with heterogeneous data. So homogeneous data is all the same data type. Heterogeneous data is different data types together. So let me trump up an example here, but there are cases where you want to do not this exact thing, but something like this. Let me, instead of declaring the colors here, I'm actually going to declare an array of colors on the shader. So this will be a constant variable. There'll be vec3s. I'll have 3 of them. And this is how we declare an array in GLSL. We say, all right, I want to make an array of vec3s, and then in here I'm going to construct a list of them. So we'll go red, there we have it, red, green, and blue. Okay. And now let's say that instead of, oh, I didn't realize that was, I guess it doesn't matter. It doesn't matter. That's fine. That works. Okay, so what I'm going to do is I'm going to take an integer and I'm going to call this color index. It doesn't matter. And now when it comes to setting the fragment color, I'll say, alrighty, let's go into that array of colors and base it on the color index that we got in. Okay, so far so good. But now let's pop back. So we'll go to the header. And now just instead of having one buffer, I'm going to have several. So I'm actually going to set this up with a vector. All right, cool. So there's that. Now I'll just go over to the constructor, and I'm going to duplicate this stuff. I'm going to rename it. So I'll have positions, and now this will be a vector of integers, which I'm going to call, let's call it color indices. And what I want is I want the first point to be color 0, then color 1, and then color 2. Okay, so a little bit of refactoring needs to happen here. The first thing I'll do is I will resize. So this just creates 2 unsigned integers in that set, and I can actually take advantage of that. So I can say, hey, I want to generate 2 buffers at once. Not that I worry about being too optimal in this creation code because it only runs once, but yeah, why not? And now just a whole bunch of little shuffling around. So it's double checking. Alrighty, so we send in the position data, and then, right, attribute pointer. I probably will change that back to a vec3. Sorry, I want to keep these sessions a little loose and flexible, but sometimes that just devolves into me rambling. But anyway, okay, so we bind the first buffer, position 0, which is going to be the position. Okay, fair enough. Send the data to the shader, the buffer, sorry. Yep, great. And now we want to enable attribute 0, which has 3 elements. They're all floats and not normalized. They now have a stride of 12 because we only need to step 3 floats to get to the next attribute vertex with an offset of 0, and they are enabled. Okay, great. Now let's do that all again. Okay, so I'm going to step through this now because this caused me some frustration. So it's a good thing to look through. Alrighty, so what I want to do is I want to create the attribute pointer to attribute 1. Now attribute 1 will have 1 thing per vertex, and it will be an integer data type with a stride of 4 because 1 int is 4 bytes with no offset. Now if we run this right now, fingers crossed it shouldn't cause any major errors, except that it does. And what have we done? It's in the deletion. Okay, no worries. So we'll just go down here and say, we could be a little more robust here, but I'm just doing it quickly. By robust, what I mean is we could set VBO's size here instead of hard coding the 2. There we go. Okay. No major errors, except that just visually it doesn't work. And this is funky and this is weird. So I had to look this up. What we need to do is not just attribute pointer, but attribute integer pointer. Now, if we were to run this, we would still get an error, so it's a great idea to just look this up. So I'll go GL, there we go. So we have size, but you can see here we don't have normalized, because why would an integer be normalized? While we're at it, why would a float be normalized? A little weird, right? But anyway, so there we have it. I can set that. There we go. Perfect. So we're now dealing with heterogeneous data. We've got float data for the positions, and we've got integer data to index into that array. And by the way, another way we could have done this is instead of using color index, we could have also used, Vertex ID. So that's just an inbuilt variable that GLSL has, which is shifted with the vertices. There we go, same thing. But we might not want that. We might want more control. And so being able to handle heterogeneous data is useful. Another thing which is useful is being able to reuse data. So let's say, for instance, I want to draw a quad. I want to cover the whole screen. How would I do that? Well, if I'm working in triangles, oh yeah, side note, the way this function works, why did I not explain this, is we have the draw mode, which in this case is triangles, and then the first vertex, then the number of vertices that we're drawing. Why did I, oh well. Okay, so how do I draw a quad one triangle at a time? Well, let me just get my right hand and position this. So we go bottom left around to bottom right, and then up. The right hand wants to go up to the top left. Okay, so let's do this again. For the next one, we'll go top left. My right hand wants to go down to the bottom right, and then up to the top right. There we go, and I'll just set these. So that was, I think it's 2, 1, 3 are the colors. Okay, now I'm going to have 6 vertices, and then if I go over to my vertex shader, I'll just give myself another color, orange. Okay, great. It's fine, it's good. We can give this a shot. Oh, yeah. Fair point. So it's saying here, and it is good to get comfortable reading these messages. So this is happening on line 24, initializer of 4 vec3s cannot be set to 3 vec3s. And what's happening here is I've created 4 of these, actually needed to declare 4 of them. Okay, give that a go. There we go. I probably messed this up a little bit. Okay, I think I see what's happened here. It's just the ordering. Okay, there we go. Perfect. So we see that we have 2 triangles filling the whole screen. But, of course, if we look back at this, we see that these vertices have been reused. Same with these ones, they've been reused. And so what we can do is something called element drawing. Funny name, but you know, element of what? Element of the buffers. So what we can do is just pop back. What I'm going to do is I'm going to declare an element buffer object, and that will store the things that we want to draw. And then I'll go right back here and I'll get rid of all the deleted data. So now I'll just make a new set, which is referring to these buffers. And I'm going to call that, element indices. And this is where I'm going to draw my stuff. So we'll pass this in, we'll say, what are we going to draw? We're going to draw vertex 0, vertex 1, vertex 2, and then we're going to draw vertex 2, 1, and 3. I said 1. Just double checking. Okay, that's fine. Okay, now it might seem a little silly right now because all I did is swap integers here for integers here, but you see that I did save a lot of memory here by reducing those floats. And of course, this isn't even anything that we can benchmark yet. This case is far too small, but when we work with larger and larger models, element drawing really makes a difference. So what we need to do now is just go right down to the bottom, and I'll grab this, and we're going to make an element buffer. Okay, so super important to make sure that we're binding it to the correct target. You could say, hey, wait a second, does it matter? Why not just bind it as an array buffer and then send the data there? Well, it doesn't matter in terms of getting the data to the element buffer, but it does matter in terms of the vertex array object, which is sitting there in the background, recording all of the state that we're setting here. So if we were to do that, the correct data would be in here, but the VAO would believe that this is just standard vertex data, that it wouldn't believe that it is element data. Okay, all right, so we'll just send. Okay, that's fine, and we don't need to create, well, there's no attributes to set, it's just data. Okay, so now what we'll do down here is we will swap this out for GL draw elements. We're going to draw triangle mode, and then this is a little bit different, so I'll just go back to draw elements, We have the mode, the number of things that we're drawing, the data type that the elements are stored in, and then this thing is a little strange. We actually don't need it. We actually don't need it because we've bound the VAO already, which has recalled the relevant data. So yeah, so let's go in and do this. Yep, so it's unsigned integer, and I'll just put in 0 for that bit there. And one last thing I'm going to do is I'm going to delete that element buffer object when the program is done. All right, quick save. Okay, fingers crossed. Let's see how this goes. Alrighty, what's happened? Oh, right. Okay. I see. I messed my calls up. So this part here, we pass the reference, not the reference, the address of that integer gets populated. And when it comes to binding, we only need the integer. Okay. Talking to myself. There we go. Excellent. So there we go. We have it. So I hope that you feel more confident working with data now, sending it to the GPU. Again, what we worked through today was a basic overview of the process, code linked down below if you want to really dig into it. We also looked at vertices and attributes, how to basically send vertex data to the GPU, how to tell the GPU what that data means and how to access it. We looked at using multiple buffers to handle different data types at the same time. And we also looked at element drawing to reuse data. Okay, I hope you had fun, and I will see you again soon. All right, bye.